The major components of our class, Logic and Computer Design Fundamentals, that we focus on are the combinational circuits and the sequential circuits. The combinational circuits, we already covered the number representations, the character representations, the logic gates, and how to write logic function, how to optimize them. And we discuss many combinational circuits and end up with the combinational circuit arithmetics in the last video. Today, we will talk about the second major component of our class, which is sequential circuit in chapter 6. It has two parts. The first part is the storage elements and analysis, and the second part is the sequential circuit design. In this video, we will discuss part 1 by talking about introduction to sequential circuit, the types of sequential circuits, the storage elements. There are 2, latches and flip-flops, and the sequential circuit analysis. And to do the analysis, which is the first component that you need to know before moving to the design, we will introduce the state tables, the state diagrams, and we will quickly check the circuit and system timing. A sequential circuit contains storage element, as you can see them in the red box, and a combinational logic, as you can see that here. The storage elements are usually the latches and the flip-flops that we will introduce today. The combinational logic implements a multiple output switching functions. It has inputs. Those inputs are signals from the outside world, and it has outputs, and they are also signals going to the outside world. They have other inputs and outputs, which are the state, or we name it present state. Those present state, or the state, they are signals that going out from the storage element and moving as inputs to the combinational logic. We have also the next state, which is going out from the combinational logic as outputs and going in as inputs in the storage element. From the storage element point of view, if we are talking about state, anything as an input to the storage element is the next state. Anything that's an output from the storage element is the present state, or simply a state. There is also another name for it, which is the current state. Now, there are 2 types of sequential circuit, milli and more. This is the general sequential circuit as we've seen. From the general sequential circuit, we have 2 types. You can see the differences are here in the inputs here and here. That's the major difference. The combinational, if we look at the combinational logic, now this combinational logic, we separate it into 2, the output logic and the input logic. Now, if we want to calculate the next state function, the next state would be a function of the inputs and the state. You can see the inputs here and also the state here. So that's for the next state function. Also here, this next state, if you want to calculate the next state, it's a function of the inputs and the state. If you want to calculate the output from this figure, you'll see that also the inputs are going in and the state is also going in. Now, if we differentiate between the input and the output logic, we will see that there is a difference in the output logic when finding the outputs. In a Milli machine, the outputs are function of the inputs and state. You can see the inputs are going in and the state is also going in the output logic. For the Moore machine, the output is only a function of the states. As you can see here in the Milli machine, in the output logic, only the states or the current state is going in as an input. And this is the major difference between the Milli and the Moore machines. The output function or the output function type depends on the specification and affects the design significantly. Let's check the types of the sequential circuit. It depends on the factor that you're trying to distinguish different types. So it depends on if you think about the times, it depends on the times at which the storage elements observe their inputs and the storage element can change their state. Based on these times, we have synchronous sequential circuit and asynchronous sequential circuit. The synchronous sequential circuit, the behavior defined from knowledge of its signals at discrete instances of time. Those discrete instances of time, we call them, or they are dominated by a clock. A clock a clock pulses are the one that's responsible for finding these discrete instances of time. Now, the storage elements observe the input and can change the state only in relation to a timing signal. This timing signal is the clock. In the asynchronous sequential circuit, the behavior defined from knowledge of inputs and at any instant of time, and the order in continuous time in which the inputs change. So whenever there is a change in the input or the state, directly the output change, and also the next state changes. If clock's just regarded as another input, all circuits are asynchronous, but it's not. The clock is actually a special signal that organizes the sequential circuit to find a predetermined discrete instances of time. Nevertheless, the synchronous abstraction makes complex design tractable. So by having a synchronous sequential circuit, the design would be easier, manageable, and tractable. The asynchronous sequential circuit is more complex and more difficult to design. Now, in order to understand the time behavior of any sequential circuit, we will introduce the discrete event simulation. And we will show it in a simple timing and table form. The rules here are the gates modeled by an ideal, instantaneous function, and another fixed gate delay. So when we mean the time is instantaneous, meaning that the output is generated right away without any delay. And then after we found the instantaneous function, we add this amount of delay after that as a fixed gate delay. This is the ideal case, meaning that it's not in real world. This never happens. Any inputs that you put in a block, it needs some time to propagate through the block and generates its outputs. Now, the second rule, any change in input value is evaluated to see if it causes a change in output value. Changes in output values are scheduled for the fixed gate delay after the input change. At the time for a scheduled output change, the output value is changed along with any inputs it drives. To show this discrete event simulation and how it works, we see it in this simple example, and we were trying to simulate a NAND gate behavior. We have a 2-input NAND gate, and the delay is 0.5 nanosecond delay. Now, we assume that A and B have been 1 for a long time as an initial case. So in the beginning, we have 1 and 1 at A and B. Now you can see that the function or the output function F is after this delay. The output here is called F instantaneous, or Fi between parentheses, as you can see here. So only after a delay of 0.5 nanosecond, Fi becomes F. So we will write the changes in the table, as you can see here. At the beginning, for a very long time. In the past, A and B were 1 and 1. In a NAND gate, if you have 1 and 1, F instantaneous will be 0. And since A and B were 1 and 1 for a very long time, F is also 0. Now we will see how the changes affect the circuit. Now, suppose that at time t equal to 0, we change A from 1 to 0, and we keep B the same. At the exact moment where t is equal to 0, F instantaneous will change directly from 0 to 1 because this is a NAND circuit. However, F will never change. It will keep its old value because we still didn't pass this 0.5 nanosecond. Only after 0.5 nanoseconds, at that time, F will change from 0 to 1. Meaning that the F followed the F instantaneous only after this amount of delay. After this, let's suppose that at time t is equal 0.8 nanosecond, A changes back to 1. Meaning now A is changing back to 1, and B will still have it the same. At this time, the instantaneous output F directly changed from 1 to 0, but F still have its output 1 from previous. Only after having a 0.5 nanoseconds, in addition to the current time, 0.8, the output F will change. Meaning after we pass 0.5, 0.8 plus 0.5 is 1.3. At that time, F will copy the F instantaneous fact. So you can see that now, even though if you didn't consider the delay, you think they are the same, they are not. F and Fi, they are affected by the delay. At some point of times, there is a change between, or the value of Fi and the value of F is different. To capture all the differences, we do this discrete event simulation. Now, suppose we have these gates, the inverter, the and the OR, with the delay represented inside the gates. We have 0.2 nanoseconds for the inverter, 0.4 nanosecond for the and 0.5 nanosecond for the OR. Now, consider this circuit. This circuit is a simple two-input multiplexer where there is a selector line. This selector line, if the selector is 0, you will choose the value of A to pass through the circuit to the output. If the S is equal to 1, you will choose B and you will pass it to the output. And this is represented, as you can see, with this function. Y is equal to A for S equal to 0, and Y is equal to B for S is equal to 1. And the function of the multiplexer is, as you can see here, Y is equal to two terms. Those two terms are A S bar and B S. B S being B and S, that these are the input of the AND. So we have B S here, and we have A S bar right here, and we OR them together to find the function. Now, what we care about in the discrete event simulation, to see the changes at the outputs, we check that using a timing diagram. Now, the timing diagram, if the input A and B were 0 and 1, and S is 0, meaning that you need to choose A and pass it to the output. So you can see that the output is 0 following the value of A. We have a delay that changed the value of S from S to S bar. This delay is the inverter delay, which is 0.2 and represented here. After some time, 0.2 nanosecond, the S can change. But before the 0.2 nanosecond here, there are still, it was still, the value was the old value. Now, for the Y, the output Y, only after you pass 0.9 nanosecond, being 0.2 here in the inverter, and 0.9, which is the addition of 0.4 and 0.5, only at that time the output is generated, and the output here is 0. So that was at the beginning. Now we will try to build build this timing diagram step by step with certain changes of the inputs. We change the inputs now to A being 0, we kept it the same. B is 1, we also kept it the same, but now S is 1. S value is equal to 1. The behavior will know that you need to choose B and pass it to the output 1. So 1 will go through the circuit and you will have it at the output. The timing diagram tells you that at this point of time, after this delay, now you changes the S here, and after the 0.2 nanosecond, the S bar is generated, and you can see the how the timing diagram excuse me. So now for the second input 0, or the second group of inputs, A being 0, S being 1, and B being 1, you can see the change. The A would be, we kept them the same. The S now we change it from 0 to 1, and the effect on S bar happens only after the 0.2 nanosecond, going from 1 to 0. Now the output will change only after passing the 0.9 nanosecond, which is the addition of those two values. And you can see that the outputs now is 1, which matches the value of B. Now, after that, we made another change. This change is having a change on A. this A, now we change it from 0 to 1. From 0 to 1. And since we make this change from 0 to 1, it's reflected in the timing diagram. And the output will change its value only after passing the 0.9, the 0.2 from the inverter and the 0.9 nanosecond going through the AND OR circuit. And you can see here that since S is equal to 1, the change in the value of A doesn't affect the output because we are still choosing the value of B. We still choosing the value of B to be in the output. Up to this point, the behavior of the circuit was normal and there wasn't anything unexpected. However, with this next change, we change the value of S, which is the control, the selection, from 1 to 0. Now, at the beginning, you think that since S is 0, we have to pass the value of A to the output. A is equal to 1, and you were thinking, expecting the value of Y is equal to 1, but no, it's not. It's still 0. Even if you were trying to figure out maybe it's B, maybe I made some mistake in the design, neither the value of A was passed to the output, nor even the value of B. So this is an unexpected behavior. This unexpected behavior was because of the delays in the circuit. This is why we need to worry about it and organize it in sequential circuit. How this happens is since we change the value of S, it was 1 before, and we change it to 0. Now, we need 0.2 nanosecond to have the change reflected in S bar. However, at that moment of time, at this window, the value of S and S bar, both of them are 0. Because we didn't pass 0.2 nanosecond yet. So the value here is 0, and the value here still 0 from the previous inputs. And because this is AND gates, this will give you 0, this will also give you 0, and the output would be 0. And so because of this delay, which is the delay of the inverter, we had a glitch in the output where the value is 0. Only after you pass this value or you pass this window, the effect will change, and you can see at that time that if you change S, if you keep S the same, and you made a change in another input, let's say B, at that time the selection being the value of S is equal to 0, you will have A in the output, where you will have the value of the output matching the value of A, which is equal to 1. And because of this, after this glitch, you will have the value equal to 1, which is the normal behavior of this circuit. You can have or change another value. I change it to 110, and you can follow the timing diagram, and you will find that the behavior of the sequential circuit is normal. So you notice there was a problem at some point because of the delay of the inverter, where we had this glitch. And this glitch was because we had this value equal to 0, and also S bar is also equal to 0 at that point of time because we didn't pass the delay yet. Now, let's connect A and Y together. So we have a feedback from the output going back to the, instead of the input A, we take it out, and we had a full feedback between Y and the first input of the AND circuit. Now the function is y would equal to b when the selection line is equal to 1, and the y of t, now we care about the time since we have a feedback. Y of t depends on the value of the output y t at the time t minus 0.9 nanosecond for s is equal to 0. So now still you are multiplexing here, you are making a choice. If s is equal to 1, you will choose b. If s is equal to 0, you will choose the value here, which is the value of y, but you still you're having a delay of 0.9 nanosecond. So the simple combinational circuits that we had before is now becoming a sequential circuit because of this feedback. And you can see the behavior or compare the behavior from the previous slide and the next slide. You will see that the timing diagram is the same. However, now in the light blue shaded area, the output y is following its previous value. So the output here is following the same output 0.9 nanoseconds ago, and so on. It's following, it's copying its value. It's copying its value up to this point. Now, at this point, there was a change in the selection line from 0 to 1. And because of this, and after you propagate through the circuits and you have some delay, after this delay, you will have the output to be matching, or the output will match the value of B, which is equal to 1. Now, we still have the same problem, this glitch. And after that, you have the select, if you have the selection line to be 0, you will have this problem, and after that you will save the old value of y here. So what we mean, because its output is a function of a time sequence of the input signals, now y is stored in the shaded area, and you can say that we saved the value of y here, and we save it or store it as well in the those shaded areas. To understand this clearly, here are some simulations with time, some input variables. The simulation example as input signal change with time right now. Now, the changes occur every 100 nanoseconds, so that the 1/10 of a nanosecond delay are negligible. So we made those assumptions to make sure that the changes are reflected in the output y. So at the beginning, if we say that the value of b is 1 and y was 0, and the selection is 0, meaning that you will select the value or the old value of y, which means that y remembers its old value 0. Now, if you made the selection is equal to 1, you will pass b to the output. Y will equal to b when s is equal to 1. If you go back and change the selection to 0, now the output y will remember its old value, which was 1. It was 1, and it remembers it and keeps it as 1. So now we save the value. We save a value. It's the circuit now has a sort of storage. Now we kept the selection to be 0. Even if we change the value of b, there won't be any change. The y still saves its old value. Now, if you change the selection and have it to 1, change it from 0 to 1, now you will select the value of b, and the value of b was 0, so you will have y equal to 0. Now, changing again from 1 to 0, y will remember its old value. And if as long as the selection lines are still 0, the value is still going to be 0, even though there is a change in the p. Those rows that we just described are the same red lines that you can see here. Let's take one of them. Let's take this one, or let's take the last three. Here, y remembered its old value. Oh, sorry, here at this row, since the selection line is equal to 1, b will be in the output. So the output would equal to the value of b, which is equal to 0. And this is why we have 0 here, up to this point. Now, we change the selection line from 1 to 0 at this point. So you can see that the selection line, it was 1, and then we change it to 0. And because of this, y would remember its old value, so it will keep having the same output value, 0. And the last row, being this line, the selection line was still the same, 0, so it's still the same, 0. But we change the value of p. The value of p, it was 0, and then we make it 1. But this change won't affect the result, because the selection line now is 0, and 0 means that I'm taking the output, the old output of y, and there won't be any changes in y when the b changes, as you can see. Now, y represent the state of the circuit, not just a normal output. Going back here, now we have the value of y here, and we have also this feedback, and then we propagate for some times, which is 0.9 nanosecond, and then we go back through the feedback. At this propagation of time, we are kind of saving the value of the circuit, or the value of y, and we are saving a state. We are saving a state of this circuit. Now, suppose we place an inverter in the feedback. So we place this inverter here. Now, here is the behavior that will happen. Now, suppose that with selection line is 1. Since the selection line is 1 in the first 2 rows, whatever the value of p, it will be reflected in the output. Now, after that point of time, we change from 1, the selection from 1 to 0. So because of this change, y will keep its old value. Y here will keep its old value. However, it will be inverted and it will be fed back here. So if at the beginning y was storing the value of 1, after 0.9 nanosecond, this one would be 0 because of the inverter. If there is a value here is 1, it will be 0 after the inverter. If it is 0, it would be 1 after the inverter. So this one will be inverted to 0. This 0 will be inverted to 1. However, because of the feedback, if you have 1, it will be inverted to 0 and go back here. Now you have a 0. It will be inverted to 1 and it will go back here. Now you have a 1, and this behavior will continue happening. So y remembers y remembering the value of a at the beginning, and after the delay, which is 1.1 nanosecond, being this delay 0.9, 0.2, 0.4, and 0.5, you notice there is an oscillation of the output. One time is 1, and then the other time is 0, and then one time is 1, another time is 0, and so on. This circuit is said to be unstable. When S is 0, notice the S is 0 here, meaning that we are having this feedback running through the circuit. The circuit has become what is called an oscillator because it's toggling from 1 to 0, 1 to 0, 1 to 0. In timing diagram, it would be like this: 1 and then 0, 1 and then 0 for a certain period of time, for a certain delay here. This delay is reflected by the feedback, which is 0.4, the 0.5, and the 0.2. So we have 1.1 nanosecond where it is 1, another 1.1 where it is 0, another 1.1 where it is 1, and so on. And this is actually could be used as a crude clock, a clock signal. It's like the heart pulse from the medical field. But for our circuit, this is our heart pulse, which is the clock. Now, we want to organize the behavior of sequential circuit. And to do this, we will introduce to you the circuitry, some basic circuits that save or store a state or store a value. So we have a basic NAND S bar dash R bar latch. There is a cross coupling between two NAND gates. If you make two NAND gates and the output is the input of the second one, and the output here of the second one is the input of the first one, and you had two inputs, one being the set input, meaning that you are trying to set the output Q to the value of 1, and we have a reset input, meaning that you are trying to reset the value of Q to 0. Now, because of this cross coupling, if the value here is 0, and let's suppose we have the value 1 and 1. If you have the value here is 0, it will come back here, and 0 and 1 in a NAND circuit becomes 1. And the 1 goes back here. 1 with 1 in a NAND circuit becomes 0, and so on. You have this behavior. The zeros go back here, becomes 1. It goes in, becomes 0. The 0 becomes 1. The 1 becomes 0. This way, you saved the value 0 in Q, and you saved the value 1 in Q bar. To see the different operation of this circuit that now can store a value. It can store a value. We say that we will change the value of R, the reset, and the S, and we want to try to find the value of Q and Q bar. Also notice here, if you know the value of Q, the Q bar is going to be the inverted value of Q. So at 1, 1, if you have the value 1 and 1, at the beginning, you cannot figure out exactly what is the value here and what is the value here, unless you assume, as we assumed here, it's 0. If it is 0, then here is 1, and it will copy, it will save the value 0 in Q. However, if it's the other way around, if the value here is 1, then it becomes 0, and you copy the value of, or you save the value of 1 in the Q. So you are not really sure. If you begin by having 1 and 1, you're not really sure what's the value of Q. It could be 0, it could be 1. Similarly, in Q bar, it could be 0 and it could be 1, because you are storing the state, but you're not sure what is it. It's unknown for you. So to make sure what exactly are the values, we have the first input combination between the S and R. If we make S 0 and R is equal to 1, this means that you are trying to set the value. Since you have a 0 here and the S, and this is called S bar, R bar, indicating that whenever the value is low, it's the active value. So when S is equal to 0, meaning that you are trying to set the value of the Q. So you will set the value here to 1. And this behaviors happen like this. If you have 1 here and 0 here, since this is a NAND circuit, you know that the value is going to be 1. Because we have 0 here. 0 after the AND is going to be 0. After the bubble is going to be 1, regardless of the second operand. So you know that the Q is equal to 1. And since the 1 going back through the cross-coupling, 1 and 1 in the NAND would be 0. And you keep it this way. You say that you set Q to 1 because S is equal to 0. Now, if you move it back to 1, the S, you moved it back to 1. After that, 1, 1 will save this value, the 1 and 0, this way. 1 will be saved to 0, and the 0 will be saved to 1. So the 1 will have the value of, the Q will have the value of 1, the Q bar will have the value of 0. So you can see that right now, we set the Q, and then we saved its value. Q is remembered because you have 1 and 1. Now, let's try to reset it. To reset it, you make the R equal to 0. If the R is equal to 0, the value of the Q bar would be equal to 1, which means that this value, this one will go here, and you have the S is equal to 1. 1 and 1, you will have it as a 0 after the snap, and you will have this behavior. You notice that the Q now is 0. So when you are trying to activate the reset, you make the value of R is equal to 0. Since this is called S dash R dash, you notice there is a dash above the R, meaning that it's going to be active when it is low. Or simply, we call it an active low reset. This is an active low reset. R is equal to 0. The 0 will generate a 0 in the Q, as you can see here. There's a 0 in the Q. So we reset. We simply say that if you have the input of the SR as 1 and 0, the reset is 0 here. So we are resetting the Q to 0. If you change the value of the R after that to 1, then you will save the value of the Q, where Q is remembered to be 0. Now, if this is the basic operation of the S dash R dash latch, or we call it a NAND latch this way. It has 2 NAND circuits, where if you have 0 and 1 in the SR, you are setting. If you have 1 and 0 in the SR, you are resetting the Q. If you have 1, 1, you save whatever was before. If you have 1, 1, you save the value of 1. If you have 1, 1 here, you save the value that you had here, 0. However, if you try to have this combination, 0, 0, if you have 0, 0, this means that you are trying to set and reset at the same time. And this is not possible in this circuit. To check this out, you can see that, let's begin here. The S is equal to 0, meaning that you have the value here, 1. And because the value here is 0, you will have the value here is also 1. and you will keep the value of the Q and Q bar 1, 1. Both of them will have a high value, but by definition, we want this one to be Q, and this one, we want it to be a Q bar. And because of this definition, we will forbid the usage of the value S equal to 0 and R equal to 0 as an input vector. And the reason it's forbidden, if after that you change the value of the 0 to 1 and this 0 to 1, so if you make this change, you will have unpredicted behavior, because this one will go here, this one will go here, and you're not sure which one you want to change to 0 first. And to get rid of this situation, we will forbid the usage of the S equal to 0 and R equal to 0. Now, we will have the other implementation of the same idea using NOR circuit. You can follow the input as I discussed it in the NAND latch, but here I'll explain it the easy way. If you have the value 0, 0, you are saving the state. If you have 0 and 1, you think I have an SR latch, meaning if I want to activate the set, it has to be high. If I want to activate the reset, it has to be high. So the reset is active high, the set is active high. Meaning if I put this input combination, S is effective because it's high, meaning that I want to set the Q to 1. The Q bar is, of course, the opposite. If I make it 1 and 0, it means that I'm resetting the value of the Q to 0. So we started as 0, 0. We are saving a value that is unknown. And then we did the set. The value of Q become 1. And then we saved it. It becomes 1. We reset. It was 0. And then we saved it. And we kept it as 0. Now, the forbidden case here is when S is equal to 1 and R is equal to 1. Now, in addition to this circuit, we will add to the NAND circuit that we discussed before, and this slide 22, we will add to this NAND circuit another part, which you can see here, 2 more NANDs. So adding 2 NAND gates to the basic S-R- NAND latch gives you what we called the clocked SR latch. This is an SR latch where you have also a control, or we call it a clock. This C, we sometimes call it control or a clock. I personally like to call it a clock all the time. Okay, now, it has a time sequence behavior similar to the basic SR latch, except that the S and R inputs are only observed when the line C, the clock line, is high. That's the idea behind this circuit. To explain it the same way, this is the clocked SR latch. Now we know that S is an active high signal, R is an active high signal. Now we can describe it this way. We have the clock signal and the S and R. If the clock signal is 0, no matter what you do to the S and R, there will be no change in the value of the Q. So the next Q, QT plus 1, is the same as the old Q of T. To check it here, if you put the value 0 here, since this is 0, this 0 will go to the NAND circuit and NAND circuit, and it will generate 1 and 1. And because you have 1 and 1 here, we describe this behavior before, and we notice that what you are doing is there is no change in the value of the Q. You keep saving the value. Now, if the control value or if the clock value is equal to 1, now you see the behavior of the SR latch. If you make it 0 and 1, meaning that you want to reset, because now the R is the active. So the value of the Q is going to be 0. If you have it as 0 and 1, that this means that you want to set. So you are setting the Q to 1. When R is equal to 1 and S is equal to 0, you are resetting, since you have a 1 here. When R is equal to 0 and S is equal to 1, you are setting the Q. Now, the value 0, 0 means the value 0, 0 in the S and R means that you are saving. There won't be any change. So there is no change. It's like when the clock equals to 0. The value 1, 1 in the SR is forbidden because the output is undetermined. This is the table that described what happens, as we can see. Now we have a current input S and R, and we have a current state Q. So we name this the current input. This is the current input. This is the current states. And this one is the next state. When you see a signal with T plus 1, this means that it's the next state. When you see a signal with only T, this means it's the current or present state. Now, after that, instead of having S and R, we combine them this way, where we have an inverter. Either you have the signal D directly, or you have it inverted. And by doing this, we are right now generating one of the most critical and important circuits in the sequential circuit, that is called a D latch. The D is in the input. It's for data, and this data you can save it through this circuit and generate it in the output. So if you add an inverter to the SR latch, this gives you the D latch, where it has three or four NAND circuits. 2 of the NAND circuits are cross-coupled, and 2 of them have a common input, which is the clock, and the other 2 operands, one of them you have it the same, and the other is inverted. Now we have the D latch truth table, where if you have the clock equal to 0, you are saving the value. If the clock input equals to 1, whatever the value of D will be generated in the Q. And this is the graphic symbol for it. It has 2 inputs and 2 outputs. The inputs are the data line D and a clock, and the outputs are Q and Q bar. Another way of looking at this table, when the D input is 0, you are resetting or cleaning the value of Q. When the data is equal to 1, you are setting the value of Q. But I like to look at it from the clock point of view. When the clock is 0, you are storing the value. Whenever the clock value is 0, you are storing. Whenever the value of the clock is 1, you are passing the value of D. Whatever the value of D becomes in the output. This is from the clock point of view. If this is the clock. Low is storing, high, you pass the value of D to the output Q. And that's one of the critical circuits, as we said. And the reason we call it a sequential circuit component is because you can store a value here. You can store a value here. Basically, whenever you have a feedback in the circuit, it must be a sequential circuit. Now, after we introduce this important circuit, we will move to the flip-flops. Now we will talk about the latch timing problem, the D latch that we just described. It has a problem. We will discuss it, and then we will find that the solution is using the flip-flops. We will introduce the edge trigger flip-flops, and we look at the standard samples, and we will see how the operation of the flip-flop also work with its time. So tell you the latch timing problem in a sequential circuit, paths may exist through a combinational logic this way, either from one storage element to another. So you will have combinational circuit, and then you will have a storage element. Let's say we have a D latch, and then a combinational circuit, another D latch, and so on. And you will see this when you move to courses that describes the computer architecture. Or from in our class, you will see this behavior here, from a storage element back to the same storage element this way. So you have a combinational logic, and after this you will have the latch, and then you go back this way. So you can see this is the feedback. The combinational logic between a latch output and a latch input may be as simple as an interconnect and nothing else. So you can take out the combinational logic completely, and it would be only a line. For a clocked D latch, or simply D latch, the output Q depends on the input D whenever the clock input has the value of 1. Same idea that we just described. If you have the C equal to 0, you are storing. Whenever it is equal to 1, you are passing the value of D. So here's one of the problems of the D latch. Suppose we have this circuit, and now we are taking the Q bar and we are feeding it to the D after an inverter. Now, initially, if the Y is equal to 0, and you have the clock this way, it was 0, and then 1, and then 0, the Y initially 0. Since this is 0, you are storing or saving. Let's say it's saving. You are saving the value. Similarly here, you will keep saving after this period where you pass the value of T. So it was 0. At this point of time, when the clock moved from 0 to 1, what happens? The value of Y was 0, meaning this one is 1. And then it goes back to the inverter. The value of Y was 0, so Q bar was 1. It goes back here, and then it becomes, after the inverter, 1. It goes through the D latch, and this becomes 1, meaning that this is a 0. And then it goes back. and this will be 1, which means this one, this will be 0, and this one will be 1, and so on. So looking at y, one time is 0, another time is 1, another time is 0, and so on. So it will keep toggling between 0 and 1, and then 0 and 1, and so on. This behavior could have only 2 times, 3 times, 4 times. It depends on what is the delay of the inverter and what is the delay inside the D-latch. So this behavior, as long as C is equal to 1, the value of Y continue to toggle or change. The changes are based on the delay presented in the loop through the connection from Y back to Y. So from this Y back to the Y again, which is this inverter and the delay in the circuit. This behavior is clearly unacceptable because we want to know what is the value of Y at any given time. The desired behavior, the Y changes only once per clock pulse. So we will accept only one change. We want only one change during this high time. You can see that there are many changes. This is one change, another change, another change, another change, and so on. So a solution to the latch timing problem is to break the closed path from Y to Y within the storage element. To do this, the commonly used path breaking solution replaced this D-latch with a flip-flop. We have master-slave flip-flop, and we also have an edge-triggered flip-flop. In this class, we will focus on the edge-triggered flip-flops. So here, this is a flip-flop solution where you have 2 D-latch. This is the first D-latch, and this one is the second D-latch. Now the Q, which is the output of the first D-latch, is the input to the second D-latch. And if you choose the clock signal to be going normally in the first, it will be inverted to the second, and vice versa. So we use an edge triggering, or we implement the edge triggering by combining a master D-latch and the slave D-latch. This is the master D-latch, and this is the slave D-latch, meaning whatever change happens in the master, the slave will copy it. An edge-triggered flip-flop triggers only during a transition of the clock signal. So whenever there is a change in the clock, meaning whenever the clock, it was 0 and then goes to 1, or it was 1 and then it goes back to 0, there will be a change in an edge trigger flip-flop. It can be built directly at the electronic circuit level as well. The change of the D flip-flop output is associated with the negative edge at the end of the pulse, meaning that you will have the change only when you have a transition. This transition, we call it a positive edge-triggered transition, or from low to high. The other change is we call it negative change, or negative edge trigger signal, where the change happens from high to low. Now, this circuit here will have one of these effective. The one that this circuit uses is the negative edge trigger, the negative edge trigger. So whenever you have this transition, the D will be observed at the Q when you have this negative edge. To know the circuit is a negative edge or a positive edge directly, you can check the inverter here. If the inverter is going to the second flip-flop, then this is a negative edge trigger clock. If this inversion is here instead of here, we take it out and we put it here, meaning that the second inverter is passing the clock signal directly, then it will be a positive edge trigger. It will be a positive edge triggered flip-flop. So this one that you see in this slide is a negative edge triggered flip-flop, meaning when you have a negative edge here, when you have a negative edge in the clock, the value of D will be observed at the Q. We also call it falling edge. Falling edge. This means that the change of the D flip-flop output is associated with the negative edge at the end of the bus, which is at this end, at this specific falling exactly. In short, if we have a clock this way, the output D will be passed through the circuit and be observed in the Q. So the passing happens only in the falling edge. Here, at this specific moment, you will have a passing. Also here, you will have passing. Any other period, here or here or here or here or here or here or here, you are storing the value. You are storing the value. So you are storing everywhere except in a single predetermined period of time, which is when exactly the value of the clock going down. This helps us solve this problem. So only when you have a falling, you will consider passing. Any other place, you will save the value of 1. A positive edge trigger, you can see that down the inverter, we move it here. And since we move it here, we always, to get the type, the correct type of the flip-flop, look at the second flip-flop. If it is passing the clock directly, then it's a positive edge trigger from low to high, or we call it rising edge trigger. Now, these are the standard samples of the circuits that we took so far. We studied the SR latch. We studied the S-R- latch. We studied their version when we connect the S and R together. So we will have D with the clock, doesn't have a bubble. And here we have a D that has the bubble. If you see now, the C, you could call it a clock or control. I prefer to call it clock. Now, in the flip-flops, we have the master-slave edged. Oh, we have the master-slave flip-flops. We have the edge-triggered flip-flops. We will only care about those versions. So we have now here a D latch where the clock goes directly. Here we have a D latch where the clock goes after inversion, where the bubble. And we have the two versions of those as flip-flops. This one is a rising edge flip-flop or a positive edge triggered flip-flop, because you don't have a bubble here. If you have a bubble here, then this is a negative edge trigger or a falling edge trigger. So it's also indicated. I will try to redraw this here. If you can see the clock from drawn like this means that it's rising edge trigger or a positive edge trigger. If you see this one here, this sample, then it means it's a negative edge trigger or falling edge trigger flip-flop. Also, you can look at it without having this sample. If you see a bubble or you don't, you can distinguish between the types of the flip-flops. If there is a bubble, meaning that this one is rising edge, this is a falling edge trigger flip-flop or has a negative pulse. This one is a rising edge trigger flip-flop because it doesn't have a bubble. So the presence of the bubbles tells you that it's a falling edge. If you remember this sentence, you will get it correctly every time. The presence of the bubble in the clock, it means that it's falling edge trigger flip-flop. Now, you can have also the D flip-flops. You know it's a flip-flop because of this samples. It's a triangle. Let's go back here so to see it. You can see here the clocks, they don't have this triangle. If you see this triangle here, it means this is an edge trigger flip-flop. It's a flip-flop, not a latch. So this is a flip-flop. This is a flip-flop. But this one is a latch, and this one is also a latch. So now we know from here that this one is a flip-flop. From this bubble, we know it's a falling edge triggered flip-flop or a negative edge triggered flip-flop. Both namings are correct. This type of flip-flop is a D flip-flop. We'll have other types later. This is a D flip-flop. And you can see here that we introduce two new signals, the S and R. So this D flip-flop, it's capable of setting or resetting the flip-flop in an initial, as an initial case. So at a power up or at a reset, all of the part of the sequential circuit usually is initialized to a known state before it begins. This initialization could be simplified or could be facilitated using the direct R and S inputs here. Now, you can see that both of them have bubble, meaning when S is equal to 0, its behavior is active. Whenever the S is equal to 0, means that I will set the D flip-flop. Setting a D flip-flop means that I'm going to have the value of 1 inside the D flip-flop. Whenever you have an R is equal to 0, means that I'm resetting this flip-flop, and resetting means that I'm having the value of 0 in the flip-flop. In another way, you could say that the S is active low, the R is also active low. So 0 is applied to the R here, resets the flip-flop to 0. If 0 applied to the S, the flip-flop will have the value of 1. Now, to understand the basic timing parity meter, we draw those three signals: the C, the clock, the D, and the Q. We have the clock 0 and then 1, 0 and then 1, and so on. The D value, since this is a negative edge triggered flip-flop, the one that we described before, the D will be observed only in the falling at this point. Then the D will be observed. It will have a meaningful value, and it will be observed in the Q after some delay. This is a delay, certain delay. So Let's see those timing definitions to understand the things that we just described. We have a setup time here. From the negative edge, there is a time just before the negative edge where the flip-flop needs sometimes to set up the values going inside the flip. It's called a setup time. We have a time after the falling edge. It's called holding time, meaning that I already take the input inside, but I need sometimes to hold the value correctly inside the flip-flop. So we call it the setup and hold time, and those two times goes together in many sequential circuits. Whenever you have this point of time where you pass the value of D to the Q, in our case, it was the falling edge, anything or the time just before that is called the setup time. The time after that is called a hold time. We have another important time, which is the TW, or the width of the clock pulse. The width of the clock pulse. So we have TW here. We also have another TW here. In an ideal case, those two TWs would be the same. However, sometimes this width is different than the other width. So we call this one is the TW high, and we have here the TW low. There is a lower bound, a minimum time allowed for the high, also a minimum time that is allowed for the low. So the TWH, the lower bound for it is this one or more. The TWL, it would be either the lower bound or more. Now, one of the important timing matrix is the propagation delay. The propagation delay, to understand the propagation delay through any sequential circuit, we need to know the time of the pulse from high to low, and we need to know the time from low to high. The time from high to low, being this time, is as you can see, from high to low, there will be certain time. Also for the other time, from low to high. From low to high, meaning if you were here from this low to this high of the clock. Now, the propagation delay is the maximum between those two lines, the maximum between those two times. So you will have a minimum time of the circuit, and you will have a maximum time. You will get the maximum from those two time, and you will consider that to be the propagation delay. To explain this also in a circuit, let's say we have this circuit where you have an OR, and you have one input inverted, and the other input, two more inputs. Let's say that they were going through an XOR, and after the XOR, going through an AND circuit this way. Now, the minimum time from the inputs, wherever that is the input, to the output, is going through the inverter this way. So that's the minimum time. The maximum time is going through the XOR, and then the AND, and then the OR. To get the propagation delay of the circuit, you consider the worst case, which is the maximum delay. So this is why the propagation delay, you take the maximum between those two times. There are many other timing parameters, and they were listed in your textbooks, but these are the important ones for us. As a summary of the memory elements, any sequential circuit, to understand it or to analyze that sequential circuit or to design the sequential circuit, you must know the components that you are working with. The first component is the D latch, and the second component is the D flip-flop. In the D latch, the state is changed when the clock is high. So when you have the clock high, you pass the D. When it is low, you store the Q. For the flip-flop, the internal state is changed only in the edge of the clock. If, for example, we take this example as a falling edge, you will pass the D on the falling edge. Similarly, if you have a positive edge. And you will store the Q anywhere else. To see this behavior in the timing diagram, in the D latch, you store when it is low, you pass the D when it is high. You store the Q when it is low, you pass the D when it is high. To check it here, notice since the clock is 0, the Q having this previous value of itself, which is low, and you keep having the low until you see the value of D of the clock is high. When it is high, whatever the value of the D is copied in the Q with certain delay. You can see that there is some delay here. When you pass this point, after some delay, whatever the value of Q that was before, you store it, you keep storing it, and you keep it here until you have the clock having a high value. When it is a high value, whatever you have in the D, it will be passed here. You can quickly look at this by checking only the passing. This is passing a 1. This is passing a 0. Anything else, you store whatever value before. So here we assume that we begin with 0, so we kept it 0 up to this point. And then we keep continuing the 1. And then we keep continuing the 0 in this part. For the D flip-flop, you only care about the edge. In our case, in this design, since you look at the second latch, you see that it is going through the inverter, so it's a falling edge. So at the falling edge, you pass. Whatever the value of D goes here, 1. Whatever the value of D, it goes here, it's 0. Any others, it starts with 0, you kept it at 0, and then it becomes 1 in the edge, and you kept it at 1. Then it falls to 0, and you kept it as 0. So you pass only at those 2 times, and you store everywhere else. From the design point of view, you have only a single D latch here. You have the D, and you have the clock in the input, the Q and the Q bar as the output. From the flip-flop point of view, you can design the flip-flop using 2 latches, where one of them is a master and the other one is the slave. And to know it, to know the type of the flip-flop, you check the position of the inverter in the connected to the second latch. Now, when the clock is high, the output follows the input in the D latch. Here, when the clock is falling, the output follows the input. After introducing the components of the sequential circuit, meaning the D latch and the flip-flop, they're usually, instead of this storage element, now we call them either D latch or a flip-flop. You can notice here we have triangle and a clock, meaning that we have an edge triggered flip-flop here. Now, the general model of the sequential circuit, we have a present state or a current state at time t. It's stored in an array of flip-flops. This could be many flip-flops or one flip-flop. They are storing the current state in the flip-flop and it's shown in the output. Now, the movement of the data is this way. So this is the input of the D flip-flop and this is the output, meaning that this is the D and this one is the Q. So you will have the Q as the present state. Whatever it's stored here, you'll see it as a present state in the Q, and it will go through the combinational logic, going back as the next state observed at the D. This is very critical and important observation. The next state, you observe it in the D of the flip-flop. So the next state at time t plus 1 is a Boolean function of a state and the input. The output at time t are a Boolean function of the states and sometimes the input. And we talked about this point when we differentiate between the milli machine and the Moore machine. As an analysis of the sequential circuit, when we try to analyze, you already have the circuit. It's already have been done. You know its block diagram. And then from the block diagram, you try to analyze the sequential circuit and understand what's going on through that circuit. To give you an example, this is a block diagram of a sequential circuit. You know that this is a sequential circuit because there is D flip-flops, as you can see. Also, there are few feedbacks. There is a feedback here, a feedback here. And because of this, you know for a fact that this is a sequential circuit. Now, how many inputs to this sequential circuit? There is a single input, X. How many outputs in this circuit? We have a single output, which is Y. And what is the state of this circuit? You have two flip-flops. And those two flip-flops together is giving you a certain state. So the state you have is A, comma B. This is your state. Now, if you were asked what is the output function and what is the next state function, the output function is the Y. So you're trying to figure out what is the Y, and you follow this logic here until you figure out what is the function. The next state function, I just mentioned in the previous slide that the next state is the next state function or the next state is connected to the D. So we have a next state here connected to this D, and we have another next state connected to this D. To differentiate between them, we will call this D A and this one D B. Now to get the functions, they are as follows. Y is equal to X bar A or B. This or one of them is going, or the input is coming from B, and the other one is coming from A. The next state function, you write it this way. You get dA, you try to get dA, and you try to get dB. Now, dA is ORing of two terms. This is an OR of two terms. The first term is X with A, AX, and the second term, X with B. This is BX. Now for the B, it has a single AND gate between the X and the A bar. Now this is one of the good points about the D flip-flop or even D latches. You have Q, both Q and Q bar. So whenever you want A, you can get it right away. Whenever you want the complement of A, you already have it in the Q bar here. So you get it right away. So the output of every flip-flop, it's generated in its normal form and in its complement form. As you can see that we generated the equation fairly easy from the block diagram. So we were able to analyze this block diagram and we generated its mathematical model being the Boolean functions. Now, if this is a timing diagram and you're trying to figure it out, you are trying to get what are the outputs. If you know that your output is the output Y, you should check only the places where there is a change based on the inputs. So to answer this question, where in time are the inputs or outputs and the states are defined? Since we have a D flip-flop, as you can see in the previous design, we only care about what happens in the flip-flop. Going back here, this flip-flop is a rising edge. This flip-flop also is a rising edge. So since we have a rising edge flip-flop, we only care about whenever the clock is rising. Whenever the clock is rising, meaning this red box. Whenever the rising points, you care about it only. And then you try to figure out what is the output Y. So for example, let's take one of them here. We know that the output Y is X bar ANDed with A or B. So let's check what is A and B. What is the value of A and what is the value of B? This is the value of A. You can see that this A here is 0. It's low. So the A is 0. Or the B is also 0. 0. And it's ANDed with X bar. The X value is 1. The X value is 1. So the complement is 0. So we end up at this point, 0 ANDed with 0 or 0. The output is going to be 0. And so on. So in the timing diagram, you would be giving everything in the top, and you will only require to find the value of Y. You should have another timing diagram for DA and DB. Sometimes they have it in the same timing diagram, sometimes they don't. It depends on the situation. The critical information that we have in this diagram is knowing when exactly the output or the state, the next state are changing, and the answer is for this specific circuit in the rising edge, only in the rising edge. Now, we have what we call a state table for the sequential circuit. The state table is actually the same as the truth table in combinational circuits. But we call it here state tables because it also includes states. The state table have a multiple variable table with the following 4 sections: present state, input, next state, and out. The present states are the values of the state variables for each allowed states. The input are the input combination allowed in the circuit. The next state is the value of the state at time t plus 1. The present state is at time t. The next state would be at time t plus 1. It's based on the present state and the input, or the next state is the function, a function of the present state and the input is always the function of those two. Now the output is a function of the present state and sometimes the input. From the viewpoint of a truth table, the inputs are the input and the present state. Both of those are inputs. The outputs are the output and the next state. Both of these two considered to be the output. Now you would understand it clearly by checking this state table. If the function dA is this one, ax or bx, the function dB is a bar x, meaning this is the next state function of the flip-flop A. This is the next state function for the flip-flop B. And an output y equal to x bar B or A. Let's say that we have those three functions for the next state and the output. Notice we have two functions for the next state. This means that we have two flip-flops. Now, how to build the state table? We have the state A and B. This is the present state, A and B. We have one input, which is an X. You find these inputs by observing what's on the right-hand side of each equation. You can notice that we have A, we have B, and we have X, and nothing else. X is the input, A and B are the present state. And then, after you figure out what are the present state and the input, you fill it as the truth table, as we explained in the truth table. The first one here, the least significant is 0, 1, 0, 1, 0, 1, 0, 1. Next one, 0, 0, 1, 1, 0, 0, 1, 1. And the last one, 0, 0, 0, 0, 1, 1, 1, 1. If you have one more, it would be 8 zeros and then 8 ones. Now, it's your job to find what is the next state and be aware of the order. You have B and A, you will have DB and DA. And you need to figure out what is the output function. You can see, let's get the DA. This is the function of the DA, which is AX or BX. Whenever the A is high and the X is high. The A is high here, and the X is high. The A is high here, and the X is high, so you have 1 and 1. That's the first term. The second term, whenever the B is high and the X is high. B is high here, and the X is high. B is high here, and also the X is high, so you have a 1 here, and you already have a 1 here. Now you know these are the ones, the rest are zeros. Similarly, for B, you care about A bar X, A bar X, this is A bar, and you have X, A bar, and X. You have 1 and 1, and the rest are zeros. For this one, is B X bar or A X bar. So you have whenever you have A with X bar, you put 1. And whenever you have B with X bar, you also have 1. This way we fill the truth table. I mentioned truth table, but in reality it's the state table. If it's a sequential circuit with the present state, the next state, then it is a state table. Sometimes you will see so many people call it also a truth table because it's behaving the same way. Another way of saying the same thing, you could have a two-dimensional table that matches well with the K-map. To do this, you would say we have a present state, and then the next state will be different based on the input. Whenever the x is 0 and the x is 1. So to do this, you could do it from the function, and I will leave this to you because it's similar to what we've seen before, or to convert it from here to there. You will distinguish between the cases when x is 0 and when x is 1. For example, for dA, when x is 0, it would be 0, 0, 0, and 0. So you go back here, and you find that when x is 0, it would be 0, 0, 0, and 0. Similarly, for the other cases, you will find it to be when x is 1, dA would be 0, 1, 1, and 1. This matches what we have here. When it is 1, you have 0, 1, 1, and 1. Another way of looking at it, you can check the next state for A this way. This is A. And here, this is dA. So it is 0, 0, 0, 1, 0, 1, 0, 1. You fill it here this way. 0, 0, 0, 1, 0, 1, 0, 1. Similarly for the B, it would be 0, 1, 0, 1, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0. And also for the output 1. So basically, this table looks shorter because we embedded the input within the next states and within the output themselves. So you can see it this way, that when the present state, when B is 0 and A is 0, you check the input. When it is 0, then dA will be like this, dB will be like this, and the output would be like this. So for an input x0, you find the next state and also the output, and so on. We use this table only when there is no space. And we want to, for example, this slide, I barely found a space for this table. Since I have some descriptions over there and I put over there and I put the function this way, I didn't have enough space, so I used this alternative state table. Personally, I like this one. It's very clear, and you can use the same methodology that we described in the truth table in the combinational circuits. Now, the state diagram, it's another tool that helps you analyze sequential circuit. The sequential circuit function can be also represented in a graphical form as a state diagram with the following components. A circle with the state name in it for each state. For example, you have this circle, and this is state S. The code of state S is 0, 0. You have also a directed arc or arrow from the present state to the next state for each state transition. So you have a direct arrow. This is an arrow from a certain present state to another next state. This is the same arrow, but represented in another way. And then you will have labels. You will have a label on each directed arc with the input values, where here x is equal to 1. This is the input. And in this arrow, it says that the output is equal to zero. Also, you have a label on each circle with the output value that is produced. So in every state, if you have /0, this means that whenever you are in this state, the output is 0. While here in this directed arrow means that whenever you are going from this present state to this next state, then the output is going to be 0. There is a short form for it this way, 1/0, meaning that this is the input and this is the output. Now, the state diagram label form on a circle with the output included. That's the state /output. It's written this way. As I mentioned, S/0, for example. More type outputs, more machines. The output depends on the state. So whenever you see a state inside when you have a state S, for example, and inside it you have /something, this means that it's following the more type. If all the states have the outputs inside them, then this machine is a more machine. Now, on a directed arc, if the directed arc has the output on them, then this is a Mealy type output. Or if the output in all the arcs, this means that this is a Mealy machine. And we will see more state diagrams now and try to check them together. If you have this state diagram, this means that this is state is 0. Its code is 0, 0. This is state is 1. Its code is 0, 1. This is state is 2. Its code 0, 1, 1, 0. And the last state is 3. Its code is 1, 1. Now, going from a certain state to another state is based on the current state, which is in the circle themselves, and the inputs. Since you can see in the arcs, we have only x equal to 0, x equal to 0 everywhere. So we have only a single input. If we have a single input, this means that each state will have 2 arrows going out of it. One arrow when x is equal to 0, another arrow when x is equal to 1. Similarly here, this is when x is equal to 1, when x is equal to 0. And you can see there are 2 arrows going out from this state, 2 arrows going out from these two, from this state, 2 arrows from this state. Now, the outputs for this state diagram are shown in the arcs. Meaning, for example, let's take this arrow. If the present state is S3, and the next state that you want, or you say it this way, if the present state is 1, 1, and the input x is equal to 0, then the next state would be 0, 0, and the output would be equal to 1. I'll do it for another state. If you are in the current state 1, 0, S2, and the input is x equal to 0, then the next state would be 0, 0, meaning S0, and the output is going to be 1. Now, if you were asked which type is this machine, since the outputs are on the arcs everywhere, then this is a Mealy machine. The diagram gets confusing for large circuits, but if you read it the same way that I explained, it should be okay. For small circuits, usually it's easy. This is considered to be a small circuit. So that's why it was easily read. Also, there are things that could be helpful to you. From the get-go, look at how many inputs you have, how many states you have, how many outputs you have, and so on. In this circuit, you have one input, you have 4 states, 4 different states. Those 4 are 0, 0, state 0, 0, state 1, 0, state 0, 1, and state 1, 1. So I have 4 states, which means that I need only 2 D flip-flops to have 4 different states. So we know the inputs, we know the states. We also look at the output. We have 1 output. Now, it's good to know the equivalent states when you try to analyze state diagrams. So 2 states are equivalent if their response for each possible input sequence is an identical output sequence. To make it easier for you, we will redefine it this way. 2 states are equivalent if and only if their outputs for each input sample are the same, and their next states for each input sample are also the same. So you have 2 states. You want to check if they are identical or not. Check their output and check their next state. If for a certain input they are the same, for all inputs cases, then they are equivalent states. To check this, let's see this state diagram. Now, I would like to ask if this state diagram, is it Mealy or more? You can see some of the arcs have outputs on them, some of them they don't. Some of the states have no outputs on them, and some have outputs. And because of this state diagram, it's neither Mealy nor more machine. Now, we have this example to show the equivalent states idea. So what happens is you try to check if a certain state is equal to another state. You check it this way. You check S0 with S1 and check if they are equivalent or not. And then check S0 with S3. Check S0 with S2. After that, you check S1 with S3. And then you check S1 with S2. And at the end, you check S3 with S2 and check for equivalence every time. Now, while we are doing this, we were at the stage where we are checking between S2 and S3. And we were checking at those. What we care about is look at this state beginning at S2. What is the next state if the input is 1? The next state is S2. For S3, what is the next state if the input is 1? The next state is the same, which is S2. That's for the first input combination. For the second input combination, when the input is 0, what happens? When the input is 0, both state S2 and S3 going to the same state S0. So the next state part is okay. This part here is okay. They are up to this point, they are equivalent. They look equivalent, S2 and S3. We need to check also the output. We need to check the output. Now, for S2 and S3, if the input is 1, We noticed that the output is 0. Good. Now, for S2 and S3, if the input is 1, we covered 1. For S2 and S3, if the input is 0, we check the output and we found that the output is 1. Notice that if the state has the output inside it, you don't have to worry about it in equivalence, because all the arcs that go into this state will have similar outputs. From that point, from that discussion, we know that S2 and S3 are equivalent, because the output for input 0 is 1 and for input 1 is 0, and the next state for input 0 is S0 and for input 1 is S2. By the definitions that we described, S2 and S3 will be equivalent. Now, we know they are equivalent. What's the value of that? The value of this is we can reduce the complexity of the state diagram. If we know that S2 and S3 are equivalent, we can take out one of them. For example, we take out this one. So how to take it out? You take it out and you have for input 0 the same output S0, and for the same next state S0, and for an input 1 the same next state, which is this state, and you name it the way you like. You could adopt one of the names, either S2 or S3, and you name it here, or a new name, call it a new state, for example. Anyway, the next state would be the same state that you have before. Actually, any one of them would be okay. And for the output, when the input is 1, the output is 0. When the input is 0, the output is 1. So notice that comparing this to the previous slide, we cross the state, and then we take out this arrow, we take out this arrow, and just to be okay, to make sure that everything is okay, take out this one and this one as well, and have only one of the states represented, and call it the name you like. You could call it S3, or you could call it S2. And then regenerate the arrows. Regenerate the arrows. To regenerate the arrows, either you copy one of them, for example, this one. So you copy this arrow with its input and output, 0 and 1. And we copy it here, 0 and 1. And then you copy one of the others arrows, either this or this. I choose this one. You know that this one going to S2. If you pick this arrow, you know that you will go to S2, which is a similar state as this S3. So you will go as a feedback. So you will go as a feedback here, 0, and the input is 1 and the output is 0. Now you do the same. You redo the equivalence again between S0 and S1, S0 and S2, S1 and S2. Checking S1 and S2, we found they are equivalent as well. S1 and S2, they are equivalent as well. To check it quickly, S1, if the input is 0, S2, if the input is 0, the outputs are 1, and the next states are the same. S1 and S2, when the input is 1, the outputs are 0, and the next state is the same, both of them going to S2. So we know S1 and S2 are equivalent. And the advantage of this is we can cross this one, this arrow, and this arrow, and we are left off with S1 only. We copy this one here, and this arrow would be a feedback to itself. It's when the output is 1, when the input is 1, the output is 0. So based on the idea of equivalence, we converted this block or this state diagram with 4 states. We converted to this simple diagram with only 2 states. Now you have a single input, X, for example, and a single output, Y, and you have only 2 states, S0 and S1. Since you have 2 states, S0 and S1, you could code them. You make this one state 0 and this one state 1. So you need only a single flip-flop. Single flip-flop. Now, to make things clearly, we discussed this before, the Moore and Millie models. Sequential circuit or sequential machine are also called finite state machine, FS. There are 2 formal models that exist, the Moore model and the Millie model. The Moore model named after E.F. Moore, the Millie model named after G. Millie. There are 2 different people. The outputs are a function of only the states. So the difference is between the output function here and here. Here, the output is a function of only the states. This is why we have in a Moore model, if you have a state, S0, let's say, you have the output along with it, being output 0 or 1. Let's say it's 1. The Millie, the outputs are a function of the inputs and the state as well. This is why the output is on the arc. When the present state is something and the input is something, then the output is, for example, 0. So you check what is the state, the current state, and what is the input. The Moore model, the outputs usually specified on the state, and the Millie model usually specified on the state transition arcs. Design way, we discussed this before, and you see the difference here in the output logic. In the output logic. Now, these are Millie and Moore examples. You can see here, since the outputs are on the arcs, this is a Millie machine. Since the outputs on the states here, this is a Moore machine. Now, note that some state diagrams are Millie, some of them are Moore, and many others are neither Moore nor Millie. Now, these are the Moore and Millie state tables. For a Millie model, you can see that you have a present state, you have a next state, when the input is 0, when the input is 1, and you have the outputs when the input is 0 and when the input is 1. For the Moore, in the output, you don't care about the input when the X is 0 and X 1. You have only an output based on the current state. That's the main difference when you look at the table. When you're trying to analyze the table, look at the output. If you see the output is differentiating between when the input is something and when the input is something else, when the input is 0, when the input is 1, the output is something, then this is Millie. If the output doesn't say anything about the input, here, it's directly because of the present state. When the present state is 0, the output is 0. When the present state is 1, then the output is 0. When the present state is 2, then the output is 1, and that's it. But here, you have to worry about what's the present state. The present state, for example, is 0, and the input is also 0, then the output is 0, and so on. Try to figure out the relationship between this state diagram and this state table. If you try and check it out, you could look at it this way. If the current state is 0 and the input is 0, the output is 0, and the next state is 0. So when the present state is 0 and the input is 0, x is equal to 0, then the next state is 0 and the output is 0. So from this arc, we got the first output and the first next state. We know that the next state is itself and the output is 0. The next state is itself, the A, whatever the A is, it's going to be the same, and the output is 0. When you write the table this way, you could write this 0 and 1, 0 and 1, 0 and 1 initial. And your job would be filling those 8 values. You fill these 8 values based on the 8 values here. This is 1, 2, 3, and 4 for the outputs. And you have 4 transitions. The end of every transition is a next state. So the total is 8. Let's say this, let's check this arc, for example, here. This says that if the current state is 0, where is the current state 0? This is the current state 0. So we're talking about this row. If the input is equal to 1, so we're talking about this column and this column, then the output, the input is 1, the output is equal to 0, and the next state going to be 1. The output is going to be 0, and the next state going to be 1. And you fill it this way. Similarly here. But the main point of this slide is the difference between the more and melee, since there are inputs in the output column, then this is melee. No inputs, this is more. This is mixed more and melee, as you can see here. This state has the output on it. Those doesn't have anything. Some of the arcs here have ones. So they are probably melee, but you find some other arcs doesn't. So this is neither melee nor more. Now, the logic diagram of any sequential circuit is this way. If you know the function of the sequential circuit, you would know the block diagram. If you know the block diagram, then you would know the sequential circuit. For this case, in this example, you have the block diagram here, and you should know what are the functions of the flip-flop. So since you have 3 flip-flops, you have 3 different next state functions. And you can see that the output here, Z, is the same as A that goes from this flip-flop. So this is flip-flop A, this is flip-flop B, and flip-flop C. Also from this sequential circuit, you will try to find inputs, and there is none. There is no inputs on this sequential circuit. Now, your job is to find the other functions. So I will try to write them here, and we will check them together. So the first one would be dA. The next, next state equation for A, which is this. You could find it starting from this point. We will find dB as well and dC. And clearly that the output function Z is equal to A. Here. Now for DA, this is DA. Sometimes you write the letter here, sometimes you write it here. DA is the ending between, you follow this line, you found that this is B, and the other line is C. So this is B, C. For the DB is going to be the OR between two terms. Those two terms are AND. So the first one is going to be C, and the other one is B bar. So the other one is B bar. Notice here that we took B and then we inverted. We could have taken out this inverter and we got the Q bar of the B and we put it here. But we were given this block diagram and we are trying to analyze it. So we are trying to figure out what are the functions. So B bar and C. The other term, quickly I'll find it, B and C bar, which is this one. Now for C, you find the AND. It's an AND, one term, only AND. And you have here A bar. We have B, A bar, sorry. This is A bar going here. So we have A bar. And we have this one is the C bar. So we have C bar. These are the equations, and for confirmation, these are the equations that we got. They are the same. We know that there is no inputs, the output is one input, Z, and we have state variables A, B, and C. Now, for those equations that we got, we want to get the state table. To get the state table, you have C, B, and A, C being the least significant, the A being the most significant, and you start filling 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, the A 0, 0, 0, 0, 1, 1, 1, 1. And for the next state functions, for each one of them is a column by itself, and you get it based on the equation as we specified before. I'll take only DA as an example. You have B, C. Whenever you have B and C, you have it in those two, B and C. So you have 1, and the rest you have it as 0. Similarly, for the DB, the DC, and also for the Z. The Z is fairly easy. It's actually a copy of the A, and this is the A here. You copy it in the Z to get the state table. Now, let's say you are given this state diagram, and you were asked which state are used. You can see that from the reset point, you will start here, and then you will go here, and then you will go here. And from here, you notice that there is only one arrow going out. So you will go here, and then you will go here. And from this point, only the one arrow going out to this one. So those 5 states are used. The other ones, this one, and this one, and this one, are not used. If you were asked, what is the function of this circuit, you worry about what happens here. So you can say that you start with 0, 0, 0, being A, B, C, and then you go to 1, and then 2, and then 3, and then 4, and then you go back to 0. So you can say that starting from the reset point, you will keep counting 1, 2, 3, and 4. And when you reach to 4, you go back to 0 and So this is what this function is performing. At this point, we finished the circuit analysis. Next time, we will talk about the sequential circuit design.